So welcome back all. So in this lecture I will talk about the rotation and vibration spectrum. So this is the 32nd lecture of quantum mechanics. So in my previous lecture I have described about the different rotational energy levels as well as different vibrational energy levels, and now in this lecture I will describe how the rotation vibration spectrum or the combination of this rotation and vibration spectrum is look like, and how the energy levels of these types of rotation vibration spectrum is look like. Those things will be covered in this lecture. So I will just briefly go through the harmonic oscillator model as well as rotation energy levels. So in harmonic oscillator level, the two atoms that is having a mass m1 and m2, they are bonded by some kinds of covalent bond, and here K is the spring constant of the covalent bond. So this spring constant actually signifies the strength of this covalent bond. The more the value of this K, more will be the strength of this bond, and R is the distance between the two atoms. So these two atoms are bonded by a covalent bond having a spring constant of K. Now the energy level for these types of diatomic molecular system can be expressed by this following formula, where En is the energy of the nth quantum states is equal to h nu into n plus half, where n is equal to 0, 1, 2, 3, all those are integer number, and this is called basically the quantum number. Now h is Planck's constant and nu is called the angular frequency. Okay, so this nu is nothing but is equal to 1 by 2 pi root over of k by mu. So all those expressions are derived in my previous lecture. So the expression of this angular frequency is 1 by 2 pi root over of k by mu, where mu is called the reduced mass of the system. So the reduced mass of the system can be expressed by this following formula, and the angular frequency nu can be also expressed by the following formula: nu is equal to c by lambda, where lambda is the wavelength, and 1 by lambda is called the wave number, that is expressed by this omega e sign. So nu is equal to c into omega e. So if we replace this nu value into by c omega e, the equation will be look like this. So this is the expression of the energy for these types of diatomic molecular system. Now suppose that the same system is there, and they are not vibrating, instead they are rotating around some common point, and this common point is called the center of mass. Okay, so the position of the center of mass I have described that depend upon the mass of these two atoms. So if mass m1 is greater than m2, the center of mass will be more inclined towards the this atom. So suppose that the distance between the center of mass and the first atom is r1, and the distance between the center of mass and the second atom is r2. So r1 plus r2 is the basically the distance between the two atoms. R is equal to r1 plus r2. For these types of model is called rigid rotor model. Okay, so in rigid rotor model, the energy levels of the rigid rotor model can be expressed by the following formula, where Ej is the energy of any jth quantum state is equal to h cross square by 2I into j plus 1, where j is called the quantum number. Its value is similar to the vibrational energy quantum number like 0, 1, 2, 3, etc. All integers value starting from 0. So here the term I is called the moment of inertia. So moment of inertia is basically acting like a mass of the substance. So instead of mass, we are taking the moment of inertia. So the expression of the moment of inertia is mu r square, where mu is the reduced mass of the system. So you can see that if we expand this equation, what we will obtain that h cross is nothing but h by 2 pi, and I is equal to mu by r square. So all those terms, if we just put down, the expression, final expression of the energy will be look like this. Now this term h by 8 pi square mu r square is replaced by a constant that is called b, or rotational constant. So the equation will be truncated into the following form. So Ej is equal to bh into j plus 1. So B is called the rotational constant, which is expressed, the unit of this rotational constant is Hertz or second inverse. Now most of the spectroscopists are more preferred to use the unit in the unit of wavelength or wave number. So that's why if we just divide this rotational constant with C, we will obtain B bar, and the unit of this B bar is centimeter inverse. So this is this B is basically replaced by this B bar term, and the equation become this one: EJ is equal to B bar HC J into J plus 1, but the unit of this B bar is centimeter inverse. So the unit of this B bar is exactly the unit of wave number. So this is the basic introduction of the harmonic oscillator model and rigid rotor model. Now in harmonic oscillator model, we have assumed that these two atoms are vibrating, but they are not rotating. And in this model, which is called rigid rotor model, we assume that the system is rotating, however the bond length is not changing. So the bond length is being fixed, they are not vibrating. Now suppose that in a system of these types of diatomic molecule, they are vibrating as well as rotating. So in that case we have to take account of this two factor. So the energy expression will not be like this or not be like this. So energy expression will be so to calculate the energy expression, we have to account for those two factor also. So this model is basically called rotational vibrational model system. So this energy expression En is equal to hc omega e into n plus half is only for vibration, and this energy expression Ej is equal to hc b bar j into j plus 1 is only for rotation. Now I have told you that suppose the molecule is rotating as well as vibrating, then the total energy of the system will be the sum of these two factor. So here you can see that hc is common in between this, so hc will be taken out of this, taken as a common term, and the equation will be look like this. Okay, now this is called the rotational vibrational energy levels. So we will see that how diagrammically or pictorially this rotational energy levels are looking like. So you can see that this is basically a parabolic curve. You can see this arises due to the vibrational this arises because it is basically a harmonic oscillator model system. So the equation of the harmonic potential energy function of the harmonic oscillator system is half kx square. So that's why this parabolic term is occurred, and you can see that the vibrational energy levels are basically equispaced. So for n is equal to 0, the energy is equal to half hc omega e. For n is equal to 1, the energy is 3 by 2 hc omega e. So you can see that the separation in between any two consecutive vibrational energy level is equal to hc omega e. Now in between the two vibrational energy level, there can be many rotational energy levels can be possible. So there are, you can see there are basically approximately 10 to 12 rotational energy levels are present in between the two vibrational energy levels. So these two will combinedly form the rotational vibrational energy levels, and this rotational energy vibration levels is looking like this. Now I will try to describe how this rotational vibrational spectrum will look like. Okay, so this is the energy expression when we have to consider both rotation as well as vibration. So the unit or the expression of this B bar will be like this: h by 8 pi square mu c r square. So here vibrational energy levels, you have to remember that the vibrational energy levels are much more bigger than the rotational energy level. So you can see that the energy or separation between the two successive vibrational energy level is much more higher compared to the rotational energy level. So in spectrum, while we are discussing about the transition in between two different energy states, the following selection rule will be followed. So for any absorption, the delta n will be always equal to +1 and delta j will be equal to ±1. So as the separation between the vibrational energy level is far more greater than the separation in between the rotational energy levels, so that's why delta n cannot be any negative value. Delta n will always be positive value, and delta j can be +1 or -1. Suppose that you can see that for this energy level, for having j is equal to 0, it can absorb energy and it can goes to j is equal to 1. Okay, so for that delta j is equal to +1. Again, sometimes it happens that for this is the energy level of j is equal to 1, and after absorption of a sufficient energy it goes to this energy level where j is equal to 0. So in that case delta j is equal to -1. So delta j can be +1 or -1, but delta n will be always +1. So this is the following selection rule that has to be followed for rotational vibrational spectrum. Okay, so you can see this is the transition in between the relative vibrational energy levels. So you can see the delta E is the expressed as the energy difference between the successive two energy levels. So this is equal to E n plus 1 j plus minus 1 minus E n j. So this delta E can be two types of delta E are possible. So for delta j equal to +1, this delta E is expressed as plus delta E, and for the transition where delta j is equal to -1, the delta E is expressed as minus delta E. So in case of delta j is equal to -1, the transition is occur from nth vibrational energy level, and the rotational energy level is j plus 1, and to this energy state it is going to n plus 1th vibrational energy level, and the rotational energy level is j. So if this transition occur, in that case delta j is equal to -1, and for delta j is equal to +1 from nth vibrational energy states and from jth rotational energy states, it is going to n plus 1th vibrational energy states and j plus 1 rotational energy states. So in that case the corresponding difference in between the two states is expressed as plus delta E. So you can see that the expression of plus delta E will be equal to the difference in between the two energy states. So this is expressed by this following equation. So the final equation of delta E plus will be hc omega E bar plus 2b bar j plus 1. So similarly you can also calculate for delta E minus, that will be equal to hc omega E bar minus 2b bar j plus 1. So all those things you can calculate. I am not going to elaborate how you can find out this expression. You can do it in your own. So you can see that there are two types of transition for from vibrational state n and rotational state j to vibrational state n plus 1 j and rotational state j plus 1. The following energy difference in between the two levels is this one, and for this types of and for a states having vibrational quantum number n, rotational quantum number j plus 1 to the states where the vibrational quantum number is n plus 1 and rotational quantum number is j, the corresponding difference in between these two states will be equal to delta E minus. So you can see that there are two types of energy difference. So that's why if you just express this energy now in terms of the wave number, so delta E is equal to h nu. So nu is equal to c by lambda. So if you just express 1 by lambda by omega bar, you will obtain nu is equal to c omega bar. So the expression of the delta E can be expressed as hc omega bar. Okay, now hc are common factor in this equation also and here also. So if we just this hc will be cancelled out, and this is basically the wavelength of the transition in between these two states. The corresponding wavelength or the wave number of the transition will be this one, and from these states to these states the corresponding wave number of the transition will be expressed as this one. Okay, so if we just draw some spectrum in the x-axis, if we put the wave number, that is 1 by lambda, in the y-axis if we put the intensity of the spectrum, we will get this types of spectrum. So this is basically a double wing spectrum, or it is also called a type of it is looking like a butterfly or double wing spectrum. And you can see that this R band is basically arising for the, delta J plus 1. Okay, so for these types of transition, you can see for these types of transition, delta J is equal to plus 1, and this band is called basically R band. And for delta J is equal to minus 1, this band is called basically P band. And this omega E is called the fundamental transition. So this omega E will be in between this two band, that is P band and R band. So you can see that this intensity is for transition 0 to 1, and this peak is for the transition 1 to 2, this peak is for transition 2 to 3, this transition is due to the this peak is due to the transition from 3 to 4. So like this. Now you can see that you can ask about the why the intensity of these types of transition is looking, why the intensity is looking like this. What is the reason behind getting these types of double humped shapes? So basically the intensity depends on the occupation of the rotational energy levels at room temperature. So this is the beyond of our discussions. If you just go through the statistical mechanics in detail, then you can understood from the statistical mechanics why the intensity pattern is following like this. Okay, so for basically this shape is depend upon how the energy levels are being separated and what is the occupation or the population of each of the energy states, and also the degeneracy of those each energy states. So all those factors will collaboratively produce this types of intensity pattern. So this is basically beyond the scope of our discussion. So for the time being, you have to understand that the shape of this R band or P band will look like this. The intensity will gradually rise up, and then at some maxima it will reach some maxima point, and then again it will gradually decrease. Okay, so this R band is arising because of these types of transition. Okay, from J is equal to 1 to J is equal to this, from J is equal to J plus 1. For these types of transition, R band is arises, and P band is arises due to these types of transition. Okay, and this omega is basically called the fundamental transition that is situated in between this two band. Okay, and you can see that the separation in between any two successive lines is equal to 2b. Okay, so you can see from this equation also you can calculate the separation in between the any two energy levels or any two intensity line, that the separation between these two will be exactly equal to 2b, where b is called the rotational constant. Now you can see this is the actual rotation vibration spectra that is looking like. You can see this is a double humped shape spectra. This is called basically R band, and this is called basically P band, and you can see in the middle there is the fundamental transition. This is basically rotation vibration spectrum for chlorine 35, and you can see that the spectra is basically split it into two parts. This is because as it is for chlorine molecule, and chlorine has two isotopes, that is chlorine 35 and chlorine 37, and chlorine 35 has abundance of almost 75% abundance, and chlorine 37 is having abundance of 25%. So due to that reason, you can also see the splitting of this line into two parts. One is for chlorine 35 and another is for chlorine 37, but they are very closely spaced to each other. Okay, and so and the gap between any successive lines will be equal to 2b. Okay, so this b will the b have the following expression that I have already described, that the b has the following expression. So you can see so if you this C term will not be there, so the expression of B will be h by 8 pi square mu r square. So this B term will depend upon the bond length of the molecule. So if the bond length of the molecule is more, the B will be less. If the bond length is less, the B will be more. So it is depend upon so the separation in between the two lines is not constant for all molecules. It changes with molecule to molecule. Now in this slide I will describe about how this microwave spectroscopy has been used to derive the bond length of any molecule or at any diatomic molecular system. So you can so I have already discussed that in case of microwave spectroscopy you will obtain these types of lines where the separation in between the two lines will be equal to 2b bar, okay, and the expression of the 2b bar will be like this. So the expression of B bar is h by 8 pi square mu c r square. So if we calculate from the microwave spectroscopy, if we calculate the value of this B bar, we can obtain the value of the bond length between these two atoms. So you can see that the expression of R will be equal to root over of h by 8 pi square B bar c into mu. So if you from the microwave spectra, if you determine the successive gap between the two lines, you can obtain the bond length of this system. So this is suppose for carbon monoxide. Suppose it is a carbon monoxide is composed of C12 isotope, and for oxygen it is composed of O16 isotope. So suppose that we obtain the microwave spectra of this carbon monoxide molecules, and from this spectra we can obtain this 2b value, which is equal to 3.8626 centimeter inverse. So the value of B bar will be equal to 1.9313 centimeter inverse, half of this value. So from this expression we can actually determine the bond length of this carbon monoxide molecule. So the value of mu will be equal to reduced mass, that is 12 into 16 by 12 plus 16 atomic mass unit, which is equal to this one, 1.13865 into 10 to the power minus 26 kg. So if you put this value of mu and P value you have already calculated from the spectrum, so if you put this all those value into this equation, you will finally obtain the bond length of this carbon monoxide molecule, that is equal to 1.128 angstrom. So you can see that microwave spectroscopy is a very important tool to determine the bond length of different diatomic molecules. So that's all from this lecture. So if you do have any questions regarding this lecture, you can ask me through the comment section. And thank you for listening to my lecture, and please follow my YouTube channel called Chembiosis, and you can also subscribe to my channel to get the latest lecture on different topics of quantum mechanics. Thank you.